Cool. So
looking at this article on paint mixing by this person. I'm not going to try to pronounce. I'm not sure how we're voicing the C. On light, colors, mixing paints, and numerical optimization. It's a short write-up that's supposed to serve as a rough description of what's going on in the paint mixing tool in this depot. So I guess there's resources here as well. So that's what Python looks like. Tool is a virtual paint mixing tool and a solver that can generate recipes for creating a particular color out of existing paints. Tool comes with data from for Chimera paints that this person measured. Tool is Python 3. Comes with all the sources. You can probably just run it. Windows executable. All that. Okay, cool. So this person recently discovered miniature painting. Yeah. Real-time graphics engineering for video games. This person does. Quickly turned out a lot of the problems that they deal with are very similar to those in miniature painting. Analyzing how light behaves, how it interacts with different surfaces, how the eyes perceive it, etc. Of course, painting is not just engineering; it's art. After all, capital A. There seems to be a consensus that painters should understand these technical aspects, even just to know when they can deliberately break them. A number of things that look like fascinating research projects somewhere between miniatures and computer graphics. The one thing that sparked interest was paints. Miniature paints usually come with cryptic names. Interesting. Don't really mind, but producers never actually tell you what those colors actually are in terms of like pigments, I guess, or like some identifier in a color space or something. When you have limited experience, it's often hard to tell if a particular paint will work as some mid-tone or if it's going to be too dark. A lot of these tutorials tell you the exact paints. They a lot of times come from different lines. Some, different supply issues. Pretty clear, instead of buying all possible paints, more reasonable approach would be to pick some base paints and learn to mix them to make the colors that this person needs. For a beginner, there are, however, two problems. Mixing is not particularly intuitive. Sometimes you get something reasonable, and sometimes you get muddy brown. That's, mixing pigments, yeah. You know what color you actually want to get, also. So some nice videos on how to color match, but if you don't have a good intuition of what skin tone you want to achieve, it's hard to tell if your mix needs more blue or red. So picking a color on the screen and knowing which paints and how to mix them, that's kind of the motivation here, I guess. Feel weird reading it in first person. Yeah, anyway. Need a model for simulating how they mix, need a numerical solver that will be able to minimize the error between the color that I want and a mix of some number of paints. Sorts of processes are something that I regularly go through and enjoy, so it looked like a perfect on-the-side project. Disclaimer here, yes, I know that in practice, no one works that way, especially if the solver gives you ratios like 88 parts of white, 3 parts of blue, and 2 parts of yellow. There's no way to mix something like this on a wet palette where you work with a minuscule amount of paint. Just, kind of, that makes sense, yeah. Still useful to know that it's mostly white with a touch of blue and yellow. So you kind of have some guidelines. And build some intuition, I guess, with experience there. So write up on the theoretical basis for a simple tool, provide it with some simple Python code. Paints. Maybe read with people with less technical backgrounds, trying to make it pretty simple and self-contained so that all information you need is here. Yeah. Cool. So light is an electromagnetic wave, oscillations of electrical and magnetic fields propagating in space. Human eyes are sensitive to wavelengths roughly between 400 and 700 nanometers. which we perceive as colors, from violet through red, green, yellow, orange, violet through blue, green, yellow, orange to red.
So these are hackers. Me.
One more time. I didn't catch that. Light usually reaches our eyes as a mixture of many different wavelengths, depending on the ratios between the amounts of particular wavelengths. We perceive the light as different colors. It consists mostly of the shorter visible wavelengths. If it's mostly shorter wavelengths, we see it as mostly blue. With longer wavelengths, it's more towards the red end of things. Yeah. To reason about these characteristics in a more principled way, one useful tool is so-called spectral power distribution. It's a function that, roughly speaking, describes how much of a particular wavelength is present in some radiation. It's usually plotted as a graph with wavelength on the horizontal axis and some energy-related quantity on the vertical axis, so that the stronger a particular wavelength is, the higher on the plot, where it's represented. So, comparison of something that's more generally blue and purple, something that's more orange and red. It's one particularly interesting family of SPDs, that is, spectral power distributions, are those from different light sources. You can take any light source and measure how much of the light it produces comes from particular wavelengths. There's this thing in physics called black-body radiation that describes the spectral power distribution of a perfectly black body so that it doesn't reflect any light, just generates it, heated to a particular temperature. All that actually led straight to quantum mechanics and the world we know today. Analyzing spectra of starlight led us to the understanding that distant stars produce energy just like the sun, and the lines appearing in the spectra of excited gases is another catalyst in the evolution of quantum mechanics. Yeah, so if you see some rating in terms of Kelvin on lights, that's what they're suggesting. It's related to a black body radiator of a given temperature. So, incandescent generally has a bias towards the infrared, and it's relatively smooth, and fluorescents have those weird peaks. Yeah, it has to do with particular, atomic something or other going on. SPD of what we consider sunlight is a fairly complex distribution that includes not only the actual spectral power distribution of the light from the sun, but also the absorption and scattering of it when light passes through the atmosphere. Because the sunlight encounters different amounts of atmosphere on its way at different times of day, sunlight also depends on time of day and atmospheric conditions. So it's having to do with how much atmosphere it's coming through, basically. There's a lot of like interference and scattering type behavior that's going on there. Because we're doing science here, everything needs to be standardized, measured, and quantified. For that reason, we've got standard illuminants, some spectral power distributions for some very particular lights. So we've got tungsten filament light bulb, black body radiator of 2856K. Illuminants B and C have become pretty much obsolete. I'm not exactly sure. That's about, D65 is neutral white. I know that's like a neutral white reference. And that's 6500K daylight. Yeah, so it roughly corresponds to black body temperature that would emit light of a similar color.
Yeah, I'm just realizing when people say the sun is a specific color, They're meaning the dominant wavelength is a specific color because the sun doesn't fluoresce at a specific wavelength. It generates a whole bunch of light across a spectrum of which a lot of it is at, 6,500 Kelvin. As you can see in the diagram that above, it's not a single wavelength, it's a whole spectrum. And black
Yeah.
body radiate at a specific wavelength that is proportional to their black body radiation, except heat is very rarely evenly distributed, so uh, it rarely produces a fluorescent like peak.
There's also, yeah, there's a lot of interesting stuff that happens as it comes through the atmosphere because it randomly
Oh
scatters
yeah,
and there's like constructive and destructive
you know,
interference that happens.
oxygen, nitrogen, carbon dioxide, all make it behave differently. Water vapor also,
Hmm.
at the lower altitudes. Um,
Yeah,
really,
different types of
nitrogen is
particles.
the big one because it's the majority component of our atmosphere. But anyways,
Yeah. Rarely see the light as it is generated by some source. Before it reaches the eye, usually bounces off of things, and we register that indirect reflected light. The way light interacts with surfaces is an incredibly complicated topic. The most basic principle is fairly simple and is described by Fresnel's equations. Light reaches the boundary between two mediums, and some of it gets reflected off the boundary, and some of it gets refracted into the object. The angle between the reflected light and the normal to the surface is the same as the angle between the incident light and the normal. How much of the light goes where and the exact direction of the refracted light depends on the index of refraction of both mediums, which is index of refraction describes the how fast light travels through that particular medium. That's a ratio of uh, compared to the speed of light in a vacuum. So it's only really valid for reflection off of a perfectly smooth mirror surface. And generally speaking, you're never going to see anything like that because there's always going to be some amount of surface features. This is only describing the first reflection off of a boundary, but it can bounce around on the microscopic structure, roughness of the surface to get into the object in a different place. Or it can do that multiple times. Go around into the object, bounce around, and go out. It's like subsurface type behavior. And this is all ignoring any kind of wave phenomena, diffraction and interference and that kind of thing. There's a lot of simplified models for understanding these things. Um, yeah, computer graphics does necessarily make some pretty significant approximations. Yeah, the from the perspective of a miniature painter, the simplest way of looking at light material interaction is to split it into two components. There are diffuse and specular components. So diffuse being, well, the specular component is everything that happens on the actual boundary between the air and the object. Some of the light bounces off. Generally, that follows the law of reflection. So the angle between the direction the light falls onto the object and the normal is the same as the angle between the direction the light is reflected at and the normal. The normal is the direction, it's the orientation of the surface. So generally, because the surface is not particularly smooth, the light will be scattered in different directions. The rougher the surface, the the more scattered it will be. That has to do with distributions of surface features. But generally happening primarily in that reflected direction. In the case of non-metals, light reflected this way does not change its colors. The reflected light will have the same spectral power distribution as the one falling on the object. Interestingly, this behavior is similar for most non-metals. To the extent that in computer graphics we often just treat all non-metal surfaces the same way, they can be rough or smooth, but they reflect the same amount of light, whether it's plastic skin or concrete. Metals, due to their atomic structure, are different. When the light reflects off of the surface and is in a specular reflection, it actually changes color. That's why gold is yellow and copper is orange. The diffuse component is all the light that goes into the object, and then some of it gets out and is generally scattered uniformly in all directions. Yeah, so that's an assumption, but generally one that holds. Doesn't matter how the surface is viewed, the diffuse lighting is the same from all angles, unlike specular, which is strongly visible when viewed from that one particular direction, and not as much with from other directions. You see it most when you're looking, yeah, at the reflected light, kind of. For nonmetals, the spectrum of the reflected light very much depends on the object. After all, the light goes into the surface, bounces around, and comes out, so it picks up some of the characteristics of the object. There's some absorption and things like that. For metals, there's no diffuse component at all. Light doesn't go out. It's either absorbed or bounces off specularly. And even though technically the diffuse component is not reflection, rather a form of scattering occurring over short distances within the material. Yeah, oftentimes say diffuse reflection for simplicity. Even though it's safe to treat the diffuse reflection as the same in all directions, brightness still depends on the amount of light falling on the given part of the object. This amount is related to the angle between the normal of the surface and the direction towards the light. The bigger the angle, the less light the given object receives. Actually, the amount of light is the same as just distributed over a larger area, which makes the light per area smaller, and this is what we consider brightness. In physics, this is called Lambert's law. I guess in painting tutorials, they talk about basic shapes in a particular way. Spheres have round shading towards the light. Cylinders have highlights along the axis, and cubes and surfaces that have generally flat lighting, depending on their orientation. Yeah, it's a practical application of Lambert's law. Spheres have smoothly changing normals in all possible directions, so their brightest area is going to be in sections facing the light. Normals of a cylinder change as you go around the circle, but are the same as you move along the axis, and the entire length of the cylinder is shaded the same. Flat planes have a constant normal, so every point gets the same lighting. Okay. Yeah, and simplified models like Phong shading, yeah, they're doing something very similar to Lambert's law here. Side note to the side note, this is of course only true if we assume that the direction towards the light is the same on the entire surface, which doesn't always hold. Yeah, so that's another approximation. For paints, we can focus on the diffuse component only. Miniature paints dry pretty matte, so the surface of the dried paint is pretty rough. The specular component of the reflection is very faint and does brighten the surface a bit with light colors, but the main characteristics of the appearance come from the diffuse part. We'll go into some theories on describing what's going on with the light in the paint layer later on, but for now we can look at the macroscopic effect. Light with some particular spectral power distribution falls onto the paint layer, and some of it gets scattered uniformly in all directions, and some gets absorbed. We can compute the ratio of that scattered light to the incident light. This is called reflexant. It's called reflectance, and just like spectral power distribution, it is a spectral characteristic. So objects that, different objects are going to reflect these different wavelengths differently. Some wavelengths are reflected more, and some are absorbed more. This is what determines the color of an object. This is if it absorbs short wavelengths and reflects and scatters long ones, it appears more red, and correspondingly, if it reflects the short wavelengths, it'd be blue. That's assuming spectral power distribution of the incident light is going to be uniform. in all wavelengths. Yeah. So it's it can be biased by whatever your light source is. If there are no long wavelengths in the incoming light and the object reflects long wavelengths, it won't look red, but it'll look black because it's not getting any light there. It's not got any light to reflect. Actual light that we see reflected is a product of the object's reflectance and the spectral power distribution of the incoming light. It's kind of like a transfer function. Not surprisingly, the same object can look very differently depending on the light used. And you can reason about the color of the object in different illumination using the above principles. If the object is blue in white light, but is illuminated by yellow or red, yellowish red candlelight, it'll appear greenish. So the next component in the system is the eye. The light that gets reflected off of objects then reaches the eye, and we can see that. In the most simplistic view, the eye focuses the light coming, incoming light into the retina, and the light-sensitive cells, rods and cones, receive that. Yeah, rods have a strongest response to the light in the green part of the spectrum, and they're responsible for seeing in low light conditions. They do not contribute to color vision, so we're not paying attention. Yeah, so the cones are they have different ranges of sensitivity in short, medium, and long wavelengths, and that's based on visible spectrum. So just like the spectral power distribution and object reflectance, we can define spectral sensitivity. It describes how strongly an eye or any other type of receiver responds to the light of a particular wavelength. It shows how excited the given type of cone is. Higher the sensitivity, the stronger the signal generated by the cone when it receives the same amount of energy. So we've got some kind of notion of where those distributions are at on the graph there. So a cone excited by the light produces a signal. The actual wavelength that caused the excitation is irrelevant. Signal will be the same if, say, M cone receives X amount of energy at 550 nanometers, and twice that amount is going to be I guess they're talking about like off peak. I guess it's going to be right. This is it. Yeah, it's basically just okay.
So it basically masks out the ultraviolet and infrared parts of the spectrum. Or am I reading ahead?
Yeah. Anyway, yeah. The now we've got the full pictures. It's emitted by some source, gets reflected by an object, and there's the reflectance. It's the transfer function there. It's registered by a cone in the eye. Yeah, so that's kind of like a convolution that's happening there with the incoming light. So you get some amount of excitation from. I guess they've got it shown here. So if you've got your fluorescent light emission spectra here, and then you've got sensitivity curve that looks like that, then you're going to get excitation that looks something like that, maybe. Because our eyes contain 3 types of cones, light generates 3 different signals that our brain interprets as color. Because there are 3 types of cones, the space of colors that people can see is intrinsically 3-dimensional. Visible colors can be described by 3 numbers instead of having to deal with the entire spectral information. I say, yes, this is where RGB comes from, but we'll get there. Well, this was heavily investigated by researchers in the early 20th century. Measuring the spectral power distribution of different lights is pretty straightforward. You split the light with a prism or some diffraction grating and look at the rainbow of colors. Measuring the reflectance is also relatively simple. You measure the spectral power distribution of some light and then shine it onto an object and measure how much is reflected. So you get a notion of how the light was transferred by way of that object. Measuring the sensitivity of the human eye is unfortunately very challenging. How would it work? It's very challenging to accurately tell if some particular light is 2 times or only 1.5 times brighter than some other light. Especially since the human vision system is incredibly complex. Rods and cones are one thing, but there's tons of processing going on in the brain that includes adaptation to light, color, and tons of other things. Color appearance models, interesting. Just further reading. Adoscope. Clever people figured out a way, so-called color matching experiments. Actual sensitivities of the eye were actually measured in the 1950s by Ragnar Granit, I think, and he was awarded a Nobel Prize for this work. That's pretty cool. The color matching experiments, person is shown a color on one side of the screen. It's a pure color generated by a light of a very narrow range of wavelengths. They then have to match that color by mixing 3 base lights on the opposite side of the screen, so that pure colors of some particular wavelengths, pure colors of some particular wavelengths, they're mixing to create some sort of matching there. And since not every pure color could be mixed from these 3 base lights, researchers added the option to add some of the mixing light to the target color, which would effectively add as a negative mixing weight. By showing people the colors for every possible wavelength of visible light, researchers measured how much of the intensity of these 3 reference lights was needed to get an impression of the same color. It's not quite the spectral sensitivity of a cell in the eye, but for practical purposes, it's just as good. We can now quantify the color of any pure wavelength as 3 numbers. And because it's linear, or any mixture made of different wavelengths can be described as some weighted sum of these triplets. So any visible color can be precisely characterized by just 3 numbers. The curves derived in color matching experiments are called RGB matching curves. The experiments were conducted in the 1920s, and back then negative numbers were a big no-no when it came to numerical calculations. But because not all colors could be matched by additive mixing, some colors required adding light to the target color, resulting in some of the values of those curves being negative. So the same CIE that standardized luminance figured out that it would be good to transform these curves mathematically so that they're always positive. This would represent the mixing of some imaginary lights that cannot exist in practice. This would mean that some of the combinations of numbers would represent colors that cannot exist, but they thought it's a good deal to get rid of these negatives. They also wanted one of the numbers to represent the general brightness of the color that responds to corresponding to the response of the rods. So math, and we get the RGB matching curves. Right, so XYZ curves are the basis of modern colorimetry. Still used today when describing the color in any scientific or technical application. There's it's the basis of the XYZ color space, where every color has 3 XYZ values and the Y is the color brightness. XYZ matching curves behave exactly like spectral sensitivities, but instead of being the sensitivities of cells in our eyes, they're just some mathematical abstract sensitivities, not describing anything in particular. Because they're just some numbers, doesn't really change anything. It's just some abstract math, yeah. So, damn, we're halfway through here. Yeah, so we went from continuous spectrum of light to 3 numbers, and we can do operations with those 3 numbers. Take light with XYZ 1 color and add it to the XYZ 2 color, and we can add them component-wise. Take light with XYZ 1 color and make it 2 times stronger. We get a doubling. So these are the types of manipulations that you would do with values in a color space. Technically, not really correct to multiply the components together. Say have the reflectance stored as XYZ and multiply it by the light XYZ, but it actually works pretty well. Yeah. Okay, so yeah, there are spectral renderers that do more elaborate calculations involving, yeah, basically just histograms of different frequencies with much more than 3 bins for red, green, and blue, or X, Y, and Z. So a fun fact, you might think that matching curves were derived after massive studies involving thousands of volunteers, but not really. Original experiments were performed by 2 people, W. David Wright with 10 observers, and John Guild with 7 observers. Interesting. Yeah, so the whole modern colorimetry is based on what 17 people saw in the 1920s. So that's a very small sample size.
It's scary, but there's probably scarier things our society is based on, so I'm not gonna worry too much about it.
Yeah. Probably true. Yeah, so we've got our curves. Later on, some revisions, most notably the 10 degrees standard observer. Okay. Later, researchers realized that due to all the adaptation in the visual system, it makes more sense for the test batches to take a larger part of the field of view. So they performed new experiments that and created new curves that are slightly different. But the 1931 curves are still most commonly used today. All the color spaces used in modern applications are derived from XYZ. So some are just linear transformations of XYZ, multiplying individual components by some constants and adding them in different combinations, like sRGB. While some involve nonlinear operations, computing powers of some expressions involving XYZ or division to make values more perceptually uniform so that differences in numbers describe similar changes in actual perceived colors, like lab. 2 important color spaces that derive from XYZ are YXY and sRGB. The first one uses Y to describe brightness and XY, which are X over X plus Y plus Z and Y over X plus Y plus Z to describe the chromacity, then just the hue and saturation of the color. Sometimes all the visible colors are visualized in the XY plane as the visual locus space of all colors that people can see. It's a convenient way of visualizing gamuts, subsets of the visible color. It can be produced in some particular way, on screen or in print. As RGB is a subset of XYZ, it's widely used in modern display technologies. Defining 3 primaries RGB used to represent the colors. Also specifies a white point, which is considered to be the point white, or the color white. Primaries are chosen so they can be physically realized in a technically feasible manner. However, the range of colors that can be represented in sRGB is somewhat limited because it relies on these base colors, and negative weights cannot be used. Monitors work by emitting light, not absorbing it. So, Ironically, the visual locus plots of all possible colors, when viewed on a screen, cannot fully display a wide range of colors. Yeah, so it's kind of a more geometric communication of the idea than it is visual specific colors. Rec 2020 and then those are used in HDR stuff. Yeah. It's important to note that RGB values only make sense within the context of a specific color space and cannot be used, cannot be transferred directly between spaces. For example, many cameras can capture photos in Adobe RGB, which is a slightly larger gamut than sRGB. To display these colors accurately on a standard monitor, they need to be converted to sRGB through some additional calculations. So the purpose of color profiles in software like Photoshop, which allow you to specify a color space you're working in and the color space of your input images, and then the software handles the conversions. There's also, if you hear optoelectric transfer function or electro-optic transfer function, those are closely related. On the other hand, CMYK, commonly used in printing, is a subtractive color space that's cannot accurately describe general light color. It's designed to describe reflectance rather than light emission. So, yeah, it's subtractive. They require the definition of a specific illuminant and how many individual components absorb and reflect light. It's not really a color space, but more of a color model, one way to practice color, a way to process color rather than a precise mathematical method for defining and operating with colors. This is generally the case with any color system based on reflected light, including painted miniatures. Coming back to that. To reason about their colors, we need to assume a certain illumination. Due to the widespread use of sRGB, D65 makes sense. So it's a cold white light. It's the objective white point in sRGB. To determine the color of a paint and display it on a screen, the full process involves taking spectral values for the D65 illuminant, multiplying by the spectral reflectivity of the paint, multiplying the result by the XYZ matching curves, and adding spectral values across all wavelengths to get XYZ values of the light. Converting XYZ values to sRGB with some simple math and displaying it on the screen. You may notice that because the integration happens across wavelengths, it's no real way to go back. Many different spectral distributions can give the same XYZ values. Yeah, metamerism, yeah. The different lighting conditions can create the same appearance. So given sRGB values, there's no straightforward way to retrieve the full spectrum back. But yeah, so the notion is here, we'd like to overcome this limitation. Cool, so pigments. Only missing bit to get the paint mixing software is a model for actually mixing the paints. You might think that we take 50% of paint A and 50% of paint B. The resulting mix would have a 50-50 mix of the reflectance of paint A and paint B, or technically that the mixing would be linear. But of course it is not. It's actually highly nonlinear, and we get something. In order to get something meaningful, we need to dive into radiative transport theory and differential equations. That's good. Previously considered the diffuse reflection as light going into the object, bouncing around and scattering a bit, being absorbed a bit, and going out. Now we look at this process in a bit more detail. Physical theory that describes a process like this is called radiative transport theory. Can describe phenomena like the blue color of sky, the color of mixed paints, more generally the effects of energy traveling through some form of medium. On the most basic level, it deals with two effects: absorption of radiation, which is light for us, and scattering. Absorption means that some of the light gets absorbed by the particles of the medium and is converted to heat. As far as light passes through the medium, there's less and less of it. It gets attenuated. Beer's law. Media that can absorb light, media that mostly absorb light appear translucent. If light goes through them, it can change color, because certain wavelengths can be absorbed more than others. But otherwise appears unchanged. If absorption is the main effect of the medium, it can be characterized by the Beer-Lambert law, which is a specific form of radiative transfer function, which states that the extinction of light is exponential with distance. The more light goes in, the more of it is absorbed in a unit distance. It's described by an exponential curve. Absorption model is fairly simple. If the light's absorbed, it's gone, and we don't have to deal with it anymore. Other effect is scattering. When a light hits a particle of the medium, it can be scattered. This is actually something I've been playing with. I can show some stuff later. Bounce off in some other direction. Yeah, so this is where the majority of the complexity comes from. Depending on the medium, the way its particles scatter light is different. Some media scatter predominantly forward, so the light direction is just slightly affected. Some scatter uniformly, so that whatever direction light comes from, it can get scattered in any other direction. On top of that, when the light is scattered, it travels further and interacts with more particles, undergoing more scattering events. So it's multi-scattering kind of a thing. And of course, it happens together with absorption. So scattered light becomes scattered more and then absorbed and so on. It results in, again, incredibly complex systems. Thousands of papers have been published on that, and yeah, complex topic. So, lucky for us, mixing colors is a pretty common problem in various industries, and it has been extensively studied. To make things a bit simpler, usually a number of simplifications are made. Instead of dealing with some general objects, people analyze transport within a very thin horizontal slab of the material. They're considered infinite to avoid having to deal with any problems on the boundaries, but that's perfectly fine. For diffuse reflection, light doesn't go very far outside to the side within the material. We also assume that the scattering function is uniform. When the light is scattered, it bounces in any random direction with no preference. For regular no-effect paints, non-metallic or iridescent or etc. kind of paints, it's totally valid. They assume some sort of circular symmetry along the vertical axis, which means that it all behaves the same no matter how we look at the surface. It's not view dependent, basically. Surface properties are the same. It's isotropic. So isotropic being the same from all directions. And the lighting is the same too. For instance, the sample is illuminated in the same way from every direction. These assumptions, you can simplify the radiative transfer equations and reason about two separate streams of lighting. One going down into deep layers, one going up, eventually leaving the paint layer. It's like going through layers of paint. Is that what they're suggesting? Yes. Given a setup like this, the radiative transport equation actually simplifies into something reasonable, solvable by hand. If you remember how to solve systems of differential equations, of course. Don't look at me. Yeah. Yeah. If on top of that you assume the thickness of the object is big enough not to pass any light through, paint it fully covered. Yeah. A fairly simple formula here. This. where K describes the absorption, S describes the scattering. Just like spectral power distributions, reflectance, and sensitivities, they're all spectrally varying, and they are different for every wavelength. This was done, although in a bit less principled fashion, in the 1920s by Kabelka and Monk, forming what is known nowadays as the Kabelka-Monk theory. It got revised later in the framework of radiative transfer theory in the form of two flux theories. Km is sort of two diffuse fluxes, and extended in 3M multiflux theories. If you're curious, there's a book by Georg Klein, I don't know, Industrial Color Physics. That sounds interesting. For practical purposes, when working with regular diffuse non-effect paints, two flux or Kabelka-Monk is generally considered enough. One thing that I don't cover here is the Saunderson corrections. These are additional factors that actually take the light specularly reflected on the surface of the paint into account and reduce the amount of light that goes into the paint layer and out of it. This is one of those rare cases where things are actually made simple. The mixing of media is linear with respect to K and S coefficients. Mixture of 50-50 paints with coefficients K1 and K2 will give half K1 and half K2, same with S. In general, we have this formulation where W1 and W2 add up to 1. It's a LERP, it's a mix. Yeah, so this equation for reflectance gives us reflectance as a function of K and S. We can rearrange it to get, for instance, K based on S and reflectance. We know how to measure reflectance, so if we only figure out where to get S from, we could compute K. Trick is take one of the paints, usually white, assume that it has S equal to 1 for all wavelengths. Then you can measure reflectance and compute K from that. So now for any other paint, well, we also need K and S, but we cannot arbitrarily set their S value to 1. However, we can mix. Yeah, I'm losing the thread here a little bit. This is yeah. Yeah, I guess we're kind of getting into.
Yeah, it seems to have been a bit of a draw the rest of the owl type situation where when it starts getting into the math of it.
Yeah. Yeah. So their idea is basically you've got some number of reference paints. Take some number of paints, preferably saturated paints, will give us a wide range of mixed colors. Take the reflectance of a fully opaque white layer, assume S for that paint is equal to 1 for all wavelengths, and derive K. White paint's generally fairly uniform and close to 1. For every other paint in the set, prepare a fully covering patch of the paint straight from the pot and mix it with white in some measured proportion. Somebody's echoing.
No, that's probably me. Sorry.
Yeah. Oh, okay. So the measure the reflectance in both patches and derive K and S for that paint. We can now take any paints in any proportions, mix their K and S coefficients. From the mix, we can compute the reflectance and convert to XYZ, later sRGB. Almost seems more straightforward to do this as a practical experience kind of painting swatches kind of thing. But yeah, anyway. Yeah, I'm not exactly tracking the math of this. I'm not a little bit
I mean,
since
it kind of seems like at some point you can just turn it into a linear combination of things. But getting to that point, you have to do a lot more work than just, oh, the color is three RGB values and I can add it all together. It's like, no, no, you can't just do that. But
kind of
I don't
derive
know
these
what that is.
distributions.
Yeah.
Yeah, so they've got this. Basically sounds like this process for deriving the distributions across the spectra, and kind of like
Yeah. Especially if they seem like they only consider diffuse right now. They don't take into account the specular aspect of things, which makes things even more complicated, I'm sure. So they're just like, no, let's not even think about it.
hmm.
But maybe I misread a previous part.
Crucial part is that the measurement, measurement of the spectral reflectance of the color samples. I need a spectrophotometer for that. Some lab grade ones and handheld ones, aiming for industry. Um, yeah, printing, that kind of thing. You could potentially use a camera, but again, that has the same limitation that it's gathering light in 3 bins RG and B, and so these have more sensitivity. They're tuned for specific wavelengths and can give you more than just 3 data points there. So do all sorts of interesting things. Have you ever looked at like hardware for you ever get a bucket of paint made, and the mixing hardware they have for that, it's done based on a sensor along those lines. Yeah. I've seen like 10 frequency bins and things like that. Yeah, you can buy the chips too if you have an application for it. It's kind of interesting. Um, no, yeah, we actually looked at this last week, didn't we? Or last time we talked about this.
Yeah, we looked at it and then described, whoa, that's a hefty price tag for what is effectively a camera that just happens to be super well calibrated and, actually accurate.
We're looking at 31 channel spectra data across the visible spectrum, so visible spectra. So that makes sense. And then different illumination sources. Okay. Huh. That's interesting. Hmm. Ceramic reference tile. Interesting. Okay. So it's a physical
Well,
object
that
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 would
actually
have.
would be very helpful to have just for like if you wanted to do it yourself with just a camera.
Yeah,
Oh,
make sure it's hitting the right. Um, getting the right values back. Yeah, that's interesting.
yeah. And the annoying thing with color is, um, spectrally speaking, if you have the spectrum, you can isolate it from the intensity, but RGB values are intensity is encoded directly into the color value. So,
I wonder how much of this is the sensitivity bands of the whatever detector, and how much of it is also takes into account like they were talking about different illumination sources, like talking about
oh yeah, getting a nice neutral light,
because they've
like
got
broad spectrum light. Because like incandescent light is actually super awesome for this because it's broad spectrum. There's no peaks or anything, but it's super power inefficient and it's, getting a nice bright daylight out of it is kind of difficult. But if you do white LEDs, they're really just yellow, red, green, and blue LEDs all combined together, which means you got nice 3 peaks rather than a separate nice spectrum distribution right there.
right, yeah. Yeah, they well, and the way that they do color LEDs, it's like either colored plastic or different colored phosphors that
Ooh,
are excited
that
by
too.
yeah
Yeah.
yeah like
It's
different
like three
colored
different
phosphors.
white. Yeah, it's like 3 different white LEDs that just get color tinted, or not even white, but like, was it blue that gets tinted white or something like that? I don't know. I
Yeah,
don't
blue
make
is
LEDs.
a common one. Yeah, that was, I think, one of the first LEDs was blue.
Red, not blue, red.
Was it? Okay.
Red, then green. Blue. Veritasium recently did a very long video, I think it was Veritasium, about the blue LED and how
Oh,
it took 20 years, 25 years post the first LEDs coming out to actually crack the manufacturing challenge, because they were able to make a couple of LEDs in like the 60s that were super faint, but they did kind of emit blue. The problem is, well, we can't just make a lab grade LED. We want to make something we can ship in products. And well, it took till the late 80s, early 90s before the guy who did it actually did crack the problem. And I think Veritasium goes over the history of it, which is kind of nice, because it's like, well, how do you develop fancy sciencey things? It's like, well, you first go to school and then work as an engineer and then blah blah blah, and actually go through the steps of it, of what he did, rather than, yeah. I'm rambling. Sorry.
well, yeah, that's yeah, I had it backwards. That's I had heard something about the blue LED before, but I guess yeah. So I guess it was later, not earlier. Yeah, approved by color experts. Was it 4 out of 5 dentists agree or something?
Yeah, I was wondering about that.
All right.
Sweet, thank you. No, I'm all good. I'm gonna take this home and eat it. Okay, thank you. You too.
Sorry. Sure. Hmm. Okay. Cool. Yeah. So.
Sorry, didn't realize I was unmuted.
It's all
Okay.
good.
He's right. Yeah. So anyway, slight tangent there. So next Spectro 2, if you're wanting to drop 12 grand or $1,200 on something for very accurately determining the color of objects. So yeah, so they've got some kind of a sensor that's, yeah, right. So it's gonna have yeah, interesting. Yeah, great. That's good. That's good. That's great. And I'm sure they'll characterize the response curves and stuff to particular wavelengths. Yeah. Interesting. It's an interesting little qualifier. It's an electrically conductive package, so be careful. Okay, cool. Yeah, all right. So I guess we're getting into, yeah, how they were doing the hardware for characterizing this stuff. Good reference lighting provided by a wide spectrum LED. Lighting below 410 nanometers and above 680 is a bit weak, making readings in those ranges less reliable. Okay, so that's probably where those violet and ultraviolet LEDs comes in, is to have an illumination source that provides excitation in those, areas where white probably isn't going to do it. Or I guess that would be infrared, the higher ranges, above 680. Anyway, instead of calibrated color samples, come with full spectral reflectance data, be able to compare it against the device there. So that's pretty cool. For my set of paints, I picked the Chimera set. Use a single pigment, and the manufacturer specifies the actual pigment itself. They are relatively consistent. So, yeah, Yeah, so it's important if you want any kind of reproducibility and consistency across. Yeah. Good. Okay. Want to complain here, but it's very much not the case for other brands of paint. Okay. Yeah. So priming a piece of plywood in black, and then painting samples for all the colors in the set on 3 centimeters by 3 centimeters, which is the measurement area of the device. And so that's going to, yeah, present it with something to measure. Okay, so yeah, some of them are translucent, especially yellow. So having to get an opaque layer takes a number of layers. Yeah, so I guess they still had some substrate poking through in some areas. We have to live with that. Professional setting of paint is applied on special drawdown charts, drawdown bar. See if it's okay. And I guess you would have information about the whatever the background is too. Okay, precise thickness, blah blah. Okay, yeah. I'm not understanding what is a drawdown bar. That's good. Yeah. Interesting.
Is it
Dr. Blaze.
basically just like a very well designed gap?
Yeah, appears that way.
Yeah, I think it's so you have like uniform thickness across the entire thing.
Okay, that makes sense.
You know, I wonder if you could get a piece of metal, like a metal bar, and then put 2 pieces of tape on either side to get that little bit of gap, and then you just do that. It might not be as precise, but it'd be certainly a lot cheaper than a piece of metal with a slight cut made into it.
Yeah, I wonder if yeah, maybe the spacing on the yeah. There's a couple ways you could do that. Yeah, some way to shim it. Yeah, if you could do it consistently, maybe like a number of sheets of paper or something. Cool. Yeah, cool. $400 for a drawdown bar. So the mix every paint with white and get exact ratios. Yeah, weight ratios. Cool. So precise scale with resolution up to 1/100th of a gram. Typically, people have those for other reasons. Resolution. So, final recipes will be given by weight, which I honestly don't think these paints differ in density too much. It's all very hand wavy, and if they do, it won't make much difference in practice anyway. Probably weigh the paint bottles from a fresh set and figure out these densities, but they didn't, and now it's too late. So we got minimum number of mixes to calculate your K and S coefficients, but having more would be better. Of course, you have more of these mixes, you need more paint, blah, blah, blah. Okay. Biggest problem is white. You need a lot, so it's good. All right. Like a real scientist, measured every patch 3 times and averaged the results. Wrote a piece of Python code, do the math for mixing K and S, and calculated reflectance and final color when illuminated by D65. Here are the spectral reflectivities of 2 paints, green and red. Excuse me. And just like you would expect, if you mix yellow and blue, you get some form of green. You've got a solver that produces a given color from a set of paints. It's all fairly straightforward. Get some set of paints, process of finding the relative amounts in the mix. Give you the color closest to the prescribed one is called optimization. Start with some mixing weights, compute the result, and analyze how to change the weights, get results somewhat closer to what we want. Rinse and repeat. Yeah, so gradient descent. Yeah, optimization problem. Okay. Getting into how we're matching the curves, loss functions, machine learning specifics. Yeah, this is fairly dense. Yeah. Sometimes using 2 paints can get you almost there, while using 3 can get you all the way there. It doesn't make sense to add an additional one to fix like 1% error. Yeah.
Makes me wonder if two paint mixing, it might not get you the exact color you want, but it also is much easier to quantify mathematically, because if you had 3 paints, you have to have 3 base colors, of which you have to put error bars on how accurate your colorimeter and lighting is. But with 2 paints, you only have to have 2 base colors. So I wonder if there's like a multiplicative effect in terms of error bars around accuracy of what the algorithm is doing versus what reality is doing. And yeah.
Yeah, sure. Yeah. Wow. So it's a tool that it's got a Qt for none and everything. That's cool. And then neat. They cannot recommend ChatGPT enough. That's cool. All right. Yeah. Okay. And then they're showing basic usage of their tool. So pretty cool. So conclusions. How does this all compare to reality? Pretty decently well, I say. Hasn't been tested super thoroughly, but you put that much amount of effort into it, you wouldn't want to test that. It's a 1-1 mix of yellow oxide and magenta. Comparing measured and predicted. Pretty close. Pretty cool. Yeah, okay, and then we got all right, different color mixes. Yeah, so pretty cool. Some lack of predictability in the yellow, I guess. Translucency of the yellow caused error. Interesting. Yeah, I wonder if we could just do it into the you look at it in the model or something as wet paint, but I guess that'd be more reflective. It would have more of a specular component if it's wet like that. It's not going to really match the usage in situ where it will dry to whatever color, whatever surface properties. Yeah, pretty cool. All the rambling, all the images not specifically mentioned below, license under Creative Commons. That's good. Yeah. Great. Yeah. They provide their email if you are curious about
Awesome.
further information. Cool.
Yeah, I like how it's a very detailed description of how the article or how the tool came about, rather than just, okay, here's a tool, here's documentation for how to use it. It's like, well, let's go into the color theory. Let's talk about paint mixing and look at what you can expect this tool to actually be able to do and possibly not do.
Hmm.
So cool. I'm gonna end the recording. So
Cool. Okay, there's your drawdown bar. You got